So in recent videos, we introduced vector spaces, and particularly we focused on subspaces. We talked about something called the subspace test, right? There are three criteria that need to be satisfied, right? Zero vector has to be in the set. You take two arbitrary vectors from the set. Their sum has to be in the set. And when you take a scalar times an arbitrary vector in the set, their scalar multiple has to be in the set. So that's the three steps for the subspace test. So here's an important result. This theorem, we're going to say the span is a subspace. The span is a subspace. So let's say you have a vector space V, and you have some vectors A1, A2 through AP in that vector space. Then the span of those vectors is what we want to focus on. The span of those vectors is itself a subspace of V. So we want to prove that, I suppose. Let's see, proof. So if we're proving it's a subspace, first of all you want to say, okay, observe, note, that the span of that set of vectors A1 through AP is a subset of V. Think about that for a second. Why is the span a subset of V? Well, remember, the span consists of all the linear combinations. So I'm taking some vectors, A1, A2 through AP, and they're in the vector space. And then I take linear combinations of those vectors. Well, any kind of linear combination has to end up back in the vector space because it's a vector space, right? So that means the span ends up in the vector space. So the span is contained in the vector space. It's a subset. Okay, so now we got to satisfy property 1, criteria 1. Now we want to show the zero vectors in the span. So let's just say note the zero vectors in the span. Now we need to justify that. If we don't justify that, then we haven't done our duty. So why is the zero vector in the span of this set of vectors A1 through AP? Since, well, think about it. The zero vector is a linear combination of those vectors, right? Since I take the zero vector, I can write it as a linear combination of A1 through AP by taking constants, right? Scalars of 0, the number 0. So take 0 times vector A1 plus 0 times vector A2. And so on and so forth. 0 times vector AP, that's going to give me back the zero vector. So yeah, zero vector is a linear combination of the AJs, we can say. So that justifies that. Now we need to take, before we go into steps 2 and 3, the sum and the scalar multiple part, we want to take two arbitrary vectors, U and V, right? In the span of that set of vectors, A1 through AP. And we want to take an arbitrary scalar. Call it R. R is our real number. It's an element of the reals. So what does U look like? Well, U is a linear combination of the AJs, right? So U is going to be some constant times A1 plus some constant, call it C2 times A2. It'd be nice if this didn't do that. Okay, there it's working. So on and so forth, some constant, call it CP times vector AP. And vector V is also going to be a linear combination of the AJs. Let's call the constants D1 times A1, then the constant D2 times A2. And then we'll keep going with that. We'll have constants all the way down to dp times vector AP. So with the CJs and the DJs are going to be real numbers, right? They're scalars. So we need just declare that the CJs and the DJs are scalars. All right, now I'm ready to do 2, which is about adding two vectors. So we're going to take U and V, those arbitrary vectors. Let's note that when you add those together, what happens? Well, imagine taking those two equations here And adding those two equations together, we're going to get what? C1 plus D1 as a scalar times vector A1. Come on, work please. Plus, let's see, we're going to have what? C2 plus D2 times vector A2, and so on and so forth. You continue that procedure until you get what? Running out of space, totally running out of space. CP plus DP times vector AP. And notice that this is just a linear combination of the AJs, right? We have a constant C1 plus D1 times the first factor, a constant C2 plus D2 times second factor, and so on and so forth. A constant CP plus DP times the P vector. So this is going to be an element of the span, right? It's just a linear combination of those vectors. So the span, it's in the span. All right, so that's 2. Now 3, we got to show what? We want to take a scalar times an arbitrary vector. So let's take R, multiply it by an arbitrary vector U, and we're going to get, so thinking about that first equation with U in it, we have RC1 times A1, RC2 times A2, so on and so forth, RCP times AP. And that is precisely a linear combination of the AJs, right? We got RC1 times the first factor, RC2 times the second factor, and so on and so forth, RCP times the P factor. So I ran out of space, so I'm just going to put an under brace here and say this is an element of the span. Span of A1 through AP. All right, so we've verified that the 3 criteria hold, right? 0 vectors in the span, sum of 2 arbitrary vectors in the span, scalar multiple for an arbitrary vectors in the span. So therefore, by the subspace property, by the subspace test, it's in the span, right? No, I'm sorry, the span is a subspace of V. By the subspace test, span of A1, A2, AP. This is not working well. Subspace of V. All right, so important result. Now, what can we do with this? Since we know that the span of any set of vectors is a subspace of the underlying vector space, this sometimes simplifies showing that something is a subspace. So we want to do an example. Exercise. Show H. H is going to be all of the vectors of the form. 5s minus 3t. 0, s plus t. So all those vectors in R3 of that form, 5s minus 3t, 0 for the second entry, s plus t for the third entry. S and t are just your real numbers. Call those the parameters. So this set is a subspace of R3. Now, let's say without using the subspace test. So we could use this through the 3-step subspace test, but we're going to say, let's not do it. Let's save some work. So, let's do a proof. So first, we're just going to note that H is a subset of R3. Why is H a subset of R3? Well, if you look at the vectors in H, they have 3 entries, right? 3 entries going down. 5s minus 3t is the first entry, second entry 0, the third entry is s plus t. So it's a subset, right? It's a subset. Now, what I'm going to do, I'm going to say we have that H, so I'm going to write down the definition of H. It's what? The set of all vectors, 5s minus 3t, 0, s plus t, such that s and t are real numbers. Now let me scroll a little. That is the same thing as, let's write this in its parametric form. This is equal to, so look, you can factor out an s, and when you factor out an s, you're going to have a vector 5, 0, 1. You can factor out a t, so you do plus t, you're going to have a vector, what, negative 3, 0, 1 for that. So where am I getting these these entries from the vectors? Those are the coefficients of the s, right? So for s, we had coefficients 5, 0, and 1. So I got, what, 5, 0, and 1 here. And for the t, I have what? Coefficients negative 3, 0, and 1. So that's what I used for. Come on. Right. Freaking right, man. Negative 3, 0, 1. All right, and this is, so that's the parametric form of your vectors. S and t are allowed to vary, right? They're allowed to be any real numbers. Now, what is this? This is what? These are just linear combinations. Linear combinations of two vectors. So this is just a fancy name for the span, right? It's the set of linear combinations of those two vectors. It's the span of 5, 0, 1 as your first vector. And for your second vector, negative 3, 0, 1. Right, so that's what that is. That's the span. So, what do we have? We have H turns out to actually be the span of two vectors. But what do we know about the span? The span is a subspace of what? R3, right? The underlying vector space. The underlying vector space is R3 because we got 3 entries in the vectors. It follows that H is a subspace of R3. Because we know spans are subspaces, right? Good. Nice result. Saved us all that work of doing the 3 steps.